Okay. So remember this. Remember this problem.
The IMO
No. So we're not doing the IMO thing yet.
Yes.
So remember this thing. If you have A and B are non-empty subsets
It's just like something
of Z mod PZ, right?
Oh wait, this is what you were asking me this morning.
Yeah. They're not empty. Remember, this was in the intermediate combi number theory lecture. So it was like A plus B is at least the minimum of P or A. Do you remember?
Oh wait, who taught this?
The dude.
Oh, Kim.
Kim Brad.
That guy.
Yeah.
Oh wait, hey, we had this taught by
It was like-
Adrian.
Oh,
He always teaches like stuff like this, and it's like scary.
Remember when you went on revenge in the what's called polynomial lecture?
Who's Adrian?
okay. So yeah. So let me read the history of this problem.
Some of my thirst of man into this.
Adrian
So
Joe Lana.
Joe. Wow.
So apparently, okay. So this is getting. Apparently, Cauchy proved this in 1813.
Whoa.
Oh.
Getting old.
Yeah,
Boomer.
as old as complex analysis.
Oh no, nightmares.
And applied to give a new proof to a lemma of Lagrange in his well-known 1770 paper.
Hell no.
See, like, what is like? It's like, yes,
Yep.
he reads papers.
Yep.
That shows that any integer is a sum of 4 squares.
Oh.
Oh, it is well known.
Wow.
So, oh yeah, that paper.
Yeah.
I don't know.
I remember the conjecture.
All right, Davenport formulated the theorem as a discrete analog of a conjecture of Kintschein or Kintscheine. I don't know how to pronounce this, which was proved a few years later by H. Mann with 2 N's.
Oh, we didn't have a teacher with the same.
Yeah, actually, there's this German sort of swear. Well, it's not a swear word, but it's like kind of like a sign of frustration. It's like money, like. And then I was playing like table tennis with this guy in the US who used to live in Germany, and every time he does something, he says money. And I was like, this doesn't make any sense. And then and then I finally got it after like 2 years. Okay, so. Okay, and then about an analog of a conjecture of Kinstein about the Schnirelmann density of the sum of 2 sequences of integers. Yeah. There are numerous extensions of this result. See, for example, reference number 45. Okay. The proofs of theorem 3.2 given by Cauchy and Davenport. Oh, this is called the Cauchy-Davenport theorem, is it? This is called the Cauchy-Davenport theorem, which has numerous applications in additive number theory. And if we can't do it in 10 minutes, we'll have to stop.
Wait, doesn't the thing start at 4:30?
Doesn't sound full.
Wait, what? Can we just not go? Can we just not go?
What do you mean?
But what did they like?
I don't know.
They
You
won't.
have to tell them that you're not gonna go after like.
Yeah. If you told them you're gonna go, then you're gonna go.
I
No,
remember.
4 to 5:30. What?
Yeah.
Why is it 1.5 hours?
That's what I said.
What did you think it was?
It is.
So the
1.5
proofs
hours.
of theorem 2 given by Cauchy and Davenport are based on the same combinatorial idea and apply induction on the size of the set B. A different algebraic proof has recently been found by the authors in reference 10 and
How
11.
recent?
Well, he wrote it in 1999, so recently maybe it could be like in the 90s.
Did you say you have to go?
What?
No. You didn't say you have to, but I feel like it is implied that you should.
What? Welcome to life.
I didn't go last week, and I'm not. I don't. My house hasn't burnt down. I still.
It's just currently burning down. Yeah, it hasn't quite burnt down yet.
You know, like they haven't
It's
found.
just been kindled.
Maybe they have it.
It's going very
Checking to
well.
see if you do it again.
Okay, and it's its main advantage. A different proof has been recently. So actually, apparently if you find a new proof of this theorem, it's worth publishing. Okay.
Yeah, research.
But I'm not sure if it's worth publishing as a paper on its own. Okay. Well, maybe like it was the first time, but now it's only one amongst 5 things. So maybe it needs to be included amongst other things. So actually, the point of this paper is that this kind of lemma or theorem is like a unified way to prove a lot of these things. Okay. Okay. So what is it saying? Easily gives several related results. As shown below, this proof can be described as a simple application of combinatorial Nordström. All right. So the first part of it, I guess, is to eliminate the min thing. Okay.
Min max.
So the claim is, what is the claim? The claim is if the size of A and the size of B minus 1 is less than or equal to P, yeah?
Then it's
Right. Or if it's bigger than or equal to P.
then it's just P because
Yeah.
because A plus B
Works.
because A plus B is still inside B.
What's
Yeah, it can't have more than P.
A plus B? This can't have more than P elements?
Because it's still in mod P.
Oh, no. Wait.
Yeah.
I'm
The
confused.
thing on the
Oh, yeah.
left side.
Yeah, it is.
Yeah, the thing on the left can't have more than P elements, right?
So that's why it's like
Yeah, so if this is bigger than P, right? Yeah. It's possible that's bigger than P, right? Then the minimum is P, right? Yeah. So if this is bigger than P, then the claim becomes is greater than or equal to P. Yeah.
Indeed.
and
Which means it's equal to P. Yeah. Okay.
Which is
So
true.
So how does the argument go? It was like something like this. If you have any G, right? So G is an element of C mod P, yeah? Then you can have you can create a set. So I guess you can create a set G minus B, yeah? That's like a set. Okay. And then you could create a set A. Yeah. And they have to intersect somewhere. Okay.
what is G an element?
Yeah, so this set, G is an element, yeah. Okay.
Why do they necessarily intersect?
Oh, okay. So it's because the size is big, right? So there has to be overlap.
Oh yeah.
Okay. So the size of this set here, right, is the same as the size of B. Yeah. So and that's the same as the size of A. So the size is too big, so they have to intersect, right? So there's something in the intersection, and it's of the form G minus B, right? But it's also of the form some A, right? So then G is equal to A plus B. Yeah. So for any G in that set, it is the sum of an A and B. So therefore, A and B has to be the whole set. Because the set of the capital A plus capital B is just the set of all things of the form A plus B. Yeah. So if any G is of that form, then Z mod PZ is a subset of A plus B. Yeah? So any G in here is also in here. Yeah.
Yeah.
So that means this is a subset of that, right?
Yep.
And so that means that has to be at least P.
Yeah, and so it's exactly P. And what about the other case?
Yeah, so the whole point of this was he said the case that the sizes are bigger than P is trivial for this reason, so we don't consider it.
Trivial.
Does that make sense?
Mm.
So basically we're just proving the case where A plus B is bigger than or equal to A plus
Plus B.
b minus 1. Yeah.
Yes.
Should we resume that another time?
Probably.
Yeah.
So we can still
Okay. Let's just stop that there.
resume. So we can resume.
But that thing wasn't that trivial.
Yeah, it was interesting enough. Yeah. But I guess it wasn't the main point of. It's trivial in the sense, I guess, like in a research paper. I mean, this is like it's like a homework exercise in a research paper.
Exercise to the reader.
Yeah. I mean, he actually told you how to do it, so it was kind of generous. But I think the paper, one of the appeals of the paper is like it's so short and everything can be understood at face value. There's no like sneaky reference. You're like, all of this depends on reference number 17, which only exists in like Toronto Library. You know, like so. Okay, so let's stop that there.
Have the sign to leave.
Okay.